In this lesson, we're going to be looking at how atoms combine to make bonds. And specifically, we're going to be using the hybrid orbital model for covalent bonding. Now, organic chemists typically visualize molecules being built using hybrid orbitals. A hybrid orbital is an atomic orbital that is formed by combining the basic atomic orbitals, that's s and p and d and f, within an atom. So hybrid orbitals are different than molecular orbitals. Molecular orbitals were made by combining atomic orbitals between atoms. Hybrid orbitals are atomic orbitals that are made by combining atomic orbitals within an atom. Now remember, orbitals are conserved. Just like what we saw with molecular orbitals, when you combine two atomic orbitals, you get two molecular orbitals. The same is true when you do it within an atom. When you combine two atomic orbitals within an atom, you're going to get two new hybrid orbitals. Now, all the hybrid orbitals that we're going to be looking at in the study of organic chemistry kind of look like p orbitals, except they're lopsided. One lobe is simply bigger than the other. So here I've got the 3D models to demonstrate that. If you combine an s orbital and a p orbital, we create a hybrid orbital. Again, see that it has two lobes, but one lobe is much, much larger than the other. Now, the energies of these new hybrid orbitals are always going to lie somewhere in between the energies of the two orbitals that you combine to make them. So let's take a look at how hybrid orbitals can be used to create bonds and make molecules. Remember, this is a model of bonding. There are other models of bonding as well. This is a pretty simple one, and it's the one that most organic chemists use because it is simple and very predictive. It's very useful. So let's take a look at a nice simple organic molecule, methane. We know a few things about methane. It has the formula CH4. It has four CH bonds, and those bonds are all the same. They have the same length and the same strength. We also know the shape of methane. It's described as tetrahedral. That word tetrahedral comes from tetrahedron, which is kind of a pyramid. If you think about the Egyptian pyramids, they actually have five total sides, right? There are four sort of exposed triangular sides, and then the bottom is actually a square. A tetrahedron is a pyramid that has a triangular bottom as well as triangular sides, which means it only has four sides. So when we say that methane has a tetrahedral shape, that means that we're placing the carbon atom in the center of that pyramid, and then the four hydrogens at the corners of the pyramid. A useful way of describing the geometry, the shape of an atom and a molecule, is to represent it using something called a bond angle. A bond angle is pretty straightforward. It just means you're taking two bonds that are sticking out of one atom and then measuring the angle between them. So in methane, if we look at the central carbon and then any two bonds emanating from it, if we measure the angle between any of those two bonds to hydrogens, the angle will always be 109.5 degrees. That's the bond angle of a tetrahedral atom. Now let's see what happens when we try to make methane using the original native atomic orbitals from each atom. So think about hydrogen. We've got four hydrogen atoms, and each one has a 1s orbital with one electron in it. The carbon atom, let's use the ground state configuration of carbon, has both first and second shell orbitals and six total electrons, four in the valence shell. So the electronic configuration of ground state carbon would look like this. Well, you can see the problem. If we're going to try to make four covalent bonds, four CH bonds, and carbon only has two unpaired electrons, then we can only make two bonds. If a covalent bond is formed from sharing electrons between atoms, then yeah, this carbon atom only has two available unshared electrons to share with hydrogen atoms. So if we made our CH bonds on ground state carbon, we would actually get a molecule that looks like this. And this is actually called carbene. But regardless, you would have two bonds, and those two bonds would be formed between an s orbital on hydrogen and a 2p orbital on carbon. And then we also would have a lone pair on that carbon, right? That would actually be the electrons in the 2s orbital of carbon, right? They're not involved in a bond, so they must be non-bonding. They're just a lone pair. Now, it's pretty obvious what we have to do. If we want to make four bonds to carbon, we need to have four unpaired electrons. And we can accomplish that by putting carbon into an excited state, right? We just lift up one of the electrons into one of those 2p orbitals, and in that excited state, we now have 4 unpaired electrons. We can then pair those 4 unpaired electrons with an unpaired electron from each of the 4 hydrogen atoms. That would make 4 bonds. So now we have the right formula, CH4. But remember, we know a few more things about methane. Not only does it have 4 CH bonds, but all 4 of those bonds are exactly the same. They have the same strength and the same length. And in this representation of methane, that's not going to be the case. Because we're making our bonds, our CH bonds, between 2 different kinds of orbitals on carbon. If you look at the drawing, you can see that. One of these bonds is drawn shorter for a reason. That shorter bond would be the bond formed when we combine an s orbital on hydrogen with the 2s orbital on carbon. The other 3 bonds are longer and weaker because those would be formed from an s orbital on hydrogen and the p orbitals on carbon. And they're longer and therefore weaker than the s to s overlap because we know that when you have more s character going into an orbital, you wind up making a stronger bond. So those 3 sigma bonds that are formed from the sp overlap are in fact going to be longer and weaker bonds than the sigma bond formed from the s to s overlap on carbon and hydrogen. So while this is closer to methane than we had originally, it's still not methane. Now, if you think about it, what we need to make 4 identical CH bonds would be 4 identical orbitals on carbon to combine with the 4 identical 1s orbitals on hydrogen. And the way we do this is to use hybrid orbitals, specifically sp3 hybrid orbitals. Here's how it works. What we're going to do is we're going to combine the 4 valence orbitals on carbon, the s orbital and the 3 2p orbitals, and essentially mix them together to create 4 new hybrid orbitals. I like to think of this as kind of like a bartender making mixed drinks, making screwdrivers, let's say. So if we imagine that our 2s orbital on carbon is a shot of vodka, and our 3 2p orbitals are shots of orange juice. If we mix all those shots together, well, we put 4 shots in, we better get 4 shots out, right? So we get 4 new orbitals in this case. What are those orbitals like? Well, again, it's like the mixed drink. It's a little bit of vodka and a lot of orange juice, which means that it's a lot like orange juice, but not quite orange juice. And these hybrid orbitals are kind of the same way. Because we combine 3 p orbitals and 1 s orbital, then the hybrid orbitals will be homogeneous. That means they're all the same, but they're going to be a lot more orange juice-like. They're going to be a lot more p orbital-like than they are s orbital-like. So these sp3 hybrid orbitals physically resemble, in terms of their shape, p orbitals. Remember, we saw this before. When you combine these orbitals, they tend to look like lopsided p orbitals. And energetically, their energies lie in between the energies of the original s orbital and the p orbitals, but closer to the original p orbitals of carbon because, well, there were more of those p orbitals going into making these hybrid orbitals. Now, hybrid orbitals are named according to the orbitals that went into making them. In this case, what we made were sp3 hybrid orbitals because it's 1 s orbital and 3 p orbitals that combine to make each one. Now that we have 4 identical valence orbitals on carbon, we can use those orbitals to make 4 identical bonds to hydrogen, which is exactly what we need for methane. So here in the drawing, you can see that I have 4 identical bonds, and we can describe them as sigma bonds because they have that circular cross section, and they're made from an s orbital on hydrogen and an sp3 orbital on carbon. So they're all the same. So what about the atomic geometry, the shape? We said that the carbon atom in methane is tetrahedral, right? And if you look at this drawing, what do the bond angles look like? As drawn, the bond angles actually look like they're 90 degrees, right? Now, technically, I could have drawn those bonds pointing at any angle I really wanted to, right? So how do we know what their actual angle is? Well, that's where valence shell electron pair repulsion theory, VSEPR theory, comes in. It explains the tetrahedral shape of that carbon atom in the middle. So those 4 bonds, those 4 pairs of electrons that are shared between carbon and hydrogens, well, they're electron pairs, and electrons are negative, and negative charges repel other negative charges. So what happens in the molecule is that each pair of electrons wants to get as far away from each other as possible while maintaining the actual bond. And the best you can do when you tie 4 things to the same centerpiece is for those things to arrange themselves into that tetrahedral shape. If you try to move any one bond away from another bond, it's going to get simultaneously closer to some of the other bonds. So this evenly spaces them at maximum distance. And that's all there is to it. The tetrahedral shape is there because the electrons simply repel each other into the most stable shape. But again, we don't draw it that way, do we? We draw it out, well, I drew it out as sort of these 90-degree angles. And it's really important to recognize that that is not right. That's fake, right? What we're doing is we're taking a three-dimensional object and drawing it into two dimensions. And when you do that, you distort it. Think about a cube. A cube is a six-sided three-dimensional object where each side is a perfect square. If you were to try to draw a cube on a piece of paper in two dimensions, it's really just a collection of lines, right? And the sides are not all squares. The front one looks like a square, but all the other ones kind of look like rhombuses, right? So yeah, when you take a 3D object and you depict it into two dimensions, it will distort itself. But you have to remember at all times when you're looking at molecules, say in a Lewis structure, the bond angles, the actual geometry, the shape is not accurately depicted. You have to recognize that it is in fact a tetrahedral shape there, even though it looks like it's square planar. So here I have a 3D model of the molecular orbitals in methane. At the center you can see that carbon nucleus, and then outside of that you can see the four little hydrogen nuclei. And then we have these sigma s to sp3 molecular orbitals bonding each carbon to each hydrogen. And you can see it has that tetrahedral shape. So the carbon atom in methane is sp3 hybridized. That's how we describe it. And that simply means that it's using sp3 hybrid orbitals to make all of its sigma bonds. And lots of molecules use sp3 hybridization. Ethane, for example, C2H6. You can imagine ethane is kind of like taking two methanes and ripping a hydrogen off each one and then kind of combining the two pieces together, right? A CH3 and a CH3. Each of the two carbons in ethane are also sp3 hybridized. And that means that all six of the CH bonds are sigma bonds that are formed between the sp3 orbital on carbon and an s orbital on hydrogen. But we now have a new kind of sigma bond, right? The carbon-carbon bond. That carbon-carbon bond is a sigma bond formed from the overlap of an sp3 orbital on one carbon and an sp3 orbital on the other carbon. Now, if you think about it for a minute, which of those types of bonds would be stronger, the CH bond or the CC bond? Well, we know that the CH bond is going to be stronger, right? For one, it has more s character. The CH bonds are made up of an s orbital and an sp3 orbital. The carbon-carbon bond is a sigma bond formed from an sp3 orbital on one carbon and an sp3 orbital on the other carbon. And that's less s character overall, meaning it's a weaker bond. Carbon is also a larger atom, right? And we know that there's a correlation to bond strength and orbital overlap with the size of an atom. The further away the valence orbitals are, the longer the bond, and that means a weaker bond. So yes, the carbon-carbon bond is weaker than those CH bonds. And that right there is a really powerful thing, because it allows us to correlate the structure of a molecule with its potential reactivity. If you think about it, if ethane were going to go through a reaction, and a reaction is nothing more than making and breaking bonds, well, what bond is most likely to break in ethane? The weakest bond. And we now know which bond is the weakest bond, right? The CC bond. Now, it's certainly possible to make other kinds of hybrid orbitals. If you think about methane and ethane, we mix together all of the valence orbitals on carbon to make our four sp3 hybrid orbitals. Let's look at how the bonding occurs in ethene. Ethene has a formula of C2H4, and it can be explained using sp2 hybridization. So on carbon, we have four valence orbitals, the s orbital and those three 2p orbitals. And with methane, we combine all four of them. But what happens if we combine only three of them? Here, we're going to combine the s orbital with two of those three p orbitals. Again, think of the bartender analogy, right? We've got our one shot of vodka, the s orbital, and now we've got three shots of orange juice, but we're only going to mix two of those shots, right? So we put three total shots into the mix, and we're going to get three shots of screwdriver back out of it. And we still have that fourth shot of orange juice, right? We got that chaser. It's unchanged, so it's still there. That 2p orbital still exists. These sp2 hybrid orbitals, again, they're going to be very much like p orbitals because we put more p orbital into the mix, right? So it's similar. We have three of those and one 2p orbital unchanged. So what does sp2 hybridization look like? Well, here's a model that shows you the orbitals all stacked up on a central atom. We've got three sp2 hybrid orbitals, and they want to get as far away from each other as possible. So they're going to point towards the corners of an equilateral triangle. Then we have that remaining unchanged p orbital, and it wants to get away from the other orbitals as much as possible, so it simply bisects it, right? It goes perpendicular to all three of those hybrid orbitals. Now, in ethene, what we have are two carbons that are bonded together, and then each carbon also is bonded to hydrogens. Using these hybrid orbitals and that leftover p orbital, we can actually describe ethene. The three sp2 hybrid orbitals, two of them go on from each carbon, two of them go on to form sigma bonds to hydrogens. The third sp2 orbital then overlaps with one of the sp2 orbitals on the other carbon. Think back to ethane, right? In ethane, we had four hybrid orbitals on each carbon, and the bond between the two carbons was made by overlapping a hybrid orbital on each carbon. So that would mean here that each carbon would have a bond to the other carbon and two bonds to hydrogen. We describe the geometry of each carbon as trigonal planar. And that means that the bond angle between HC and H or HC and C is roughly 120 degrees. Now, if you think about it, each carbon still has that leftover unhybridized p orbital. And when we bring these two carbons together in space to make that sigma bond between the two hybrid orbitals, it perfectly aligns the p orbitals on each carbon to make a pi bond, a side-by-side overlap of those lobed p orbitals. And that means that there are actually two bonds between the carbons in ethene. We call that a double bond. So if we draw a Lewis structure of ethene, we would actually place two bonds, two lines drawn between the two carbons. And this can actually be a bit misleading because if you think about it, even though we draw those two bonds identically, they're not actually the same. Those are two different kind of bonding interactions. One of those bonds is formed between a hybrid orbital on one carbon and a hybrid orbital on the other carbon. That's a sigma bond. But the second bond is actually a pi bond from the side-by-side overlap of a p orbital from each carbon. And of course, the CH bonds are going to be from the s orbital on hydrogen overlapping with a hybrid orbital, an sp2 hybrid orbital from each carbon. Now let's stop and think about this again for a second. What we have here in ethene are three different kinds of bonds, right? We have two kinds of sigma bonds and then the pi bond. And we can predict which of those bonds is in fact the weakest. It's the pi bond, right? The carbon-carbon pi bond. It has no s character whatsoever, and it's a pi bond, and pi bonds are weaker than sigma bonds. And again, that is a prediction of how this molecule might react. If you react ethene, it's the weakest bond that's going to wind up breaking in a reaction, and that's the pi bond, and that's exactly how ethene and related molecules react. Well, you can probably see where we're going with this. If we can combine all four valence orbitals to create sp3 hybrid orbitals, and we can combine three of the valence orbitals to create sp2 hybrid orbitals, then yeah, we can combine one of the s orbitals with just one of the p orbitals and create sp hybrid orbitals. And that's what we're going to use to explain the bonding in ethyne. Ethyne has a formula of C2H2. Now, let's take one of those carbons and mix together the s orbital and one of the two p orbitals. That would create two new hybrid orbitals, right? These are going to be sp hybrid orbitals. And we still have those leftover p orbitals, right? They didn't change. So what does sp hybridization look like? Well, here is a 3D model showing you the orbitals involved. We have our two hybrid orbitals, right? The sp hybrid orbitals, and they want to get as far away from each other as possible. So they're going to point in opposite directions, 180 degrees from one another. Then we have those two remaining p orbitals, right? And they're going to want to get as far away from each other as possible as well. So they're going to be perpendicular to one another and perpendicular to the two sp hybrid orbitals. So just like we saw in ethane and ethene, we're going to wind up forming a carbon-carbon sigma bond using a hybrid orbital, an sp hybrid orbital, from each carbon. And then the other hybrid orbital will make a CH bond, again on each carbon. Now, each of the carbons also has two remaining 2p orbitals, right, that are unchanged. So what can happen is that one p orbital on one carbon can overlap with another p orbital on another to create a pi bond. but it can do it twice because there are two p orbitals on each carbon. That means we now make three total bonds between the carbons, a sigma bond between sp hybrid orbitals, and two p to p overlaps, creating two pi bonding interactions. So three bonds means a triple bond between the carbons. So when we draw out a Lewis structure for ethyne, we can see that we have three bonds drawn between the two carbons. But similar to what we saw with ethene, while we draw those three bonds looking identically, they're in fact not the same. One of those bonds is a sigma bond, and the other two are in fact identical pi bonds. Now, the overall shape of ethyne is linear. All four atoms are actually in a straight line. And once again, the valence shell electron pair repulsion theory kind of gets us to that shape. Each carbon has two hybrid orbitals that want to point in opposite directions to get away from each other, and that makes the p orbitals overlap to create those pi bonds. So it has a linear geometry. sp hybridization has bond angles of 180 degrees. A critically important skill when studying organic chemistry is to be able to look at a molecule and the individual atoms in that molecule and determine the hybridization on each atom. This is something you're going to be doing all the time when studying organic chemistry, so being able to do it correctly and quickly is really important. Now, there are a few ways this can be done, so I'm going to show you the way I like to do it. And I start off by just assuming that an atom is sp3 hybridized, because that's actually the most common form of hybridization in an atom. Of course, remember that hydrogen can't hybridize. It only has one orbital, so it can't mix its orbitals with itself, right? So we start with sp3 hybridization, and then we look for things that change it to either sp2 or sp. So there are two things you want to look for. One of them is pretty easy, and that is pi bonds. You might have figured out now that when you have double and triple bonds, one of those bonds is a sigma bond, and then the other parts of that are pi bonds. So a double bond has a sigma and a pi, and a triple bond has a sigma and 2 pi. So finding pi bonds is actually very easy, right? You're looking for double and triple bonds. So what you want to do is look at an individual atom, start by assuming it's sp3, and then counting how many pi bonds, if any, are connected to it. And for each pi bond, you lower that p character down by 1. So if it has one pi bond, it goes from sp3 to sp2. The other thing you need to look for is a little more complicated, and that is you need to look for unfilled orbitals on a given atom. So how do we know if there's an unfilled orbital on an atom? Well, you have to really draw the Lewis structure, at least for that atom. The whole molecule doesn't have to be a Lewis structure, but you've got to make sure that the charges and any lone pairs are drawn correctly on that specific atom. So let's look at a handful of examples. Let's start with the molecules we've already dealt with: methane, ethene, and ethyne. If we look at the carbon atom in methane, we can see that there are no double or triple bonds on the carbon, so there are no pi bonds. We can also count the total number of electrons on that carbon. And here I'm talking about counting electrons for valency purposes, which means all the electrons. Now there are 4 bonds sticking out of that carbon, so that's 4 pairs, that's 8 electrons. Now carbon is a second shell element, which means it has 4 valence orbitals, which can contain 8 electrons. And that means that the valency is filled here. There are no unfilled orbitals. So we leave it as sp3. The carbon in methane has no pi bonds, and it has no unfilled orbitals, so it stays sp3. If we look at either of the carbons in ethene, well, we can immediately see a double bond, and that means that each carbon has a pi bond attached to it. So we knock that p character down by 1 tick, right? So now it's not sp3, it's sp2. And then we look for unfilled orbitals. And either of those carbons, if you look at it, each one has 4 pairs of electrons surrounding it. And again, carbon being a second shell element has 4 valence orbitals. That's 8 electrons, and that's exactly what this has. So no unfilled orbitals, we leave it at sp2. If we look at ethyne, either of the carbons in this molecule, we can see that each one's involved in a triple bond. And a triple bond has 2 pi bonds. So because there are 2 pi bonds attached to either of these carbons, we have to knock that p character down twice, down to sp. Now, each of these carbons has 4 total bonds attached to it. That means 4 pairs of electrons. Again, that's an octet, so the outer valency is filled. There are no unfilled orbitals, so we leave it at sp. Where determining hybridization gets a little more complicated is when there are charges and lone pairs involved. So let's take a look at this molecule, ammonia, NH3. Now, if you look at NH3 in and of itself, There is, in fact, a lone pair on that nitrogen, whether it's drawn or not. And this can be a dangerous thing. If you were given a KEKULE structure of ammonia, you have to recognize that that lone pair is there even if it's not drawn. And again, you know it's there because you can look at the periodic table. You can see that nitrogen is in the fifth column. It needs 5 electrons, therefore, for charge counting purposes to be neutral. And without that lone pair, it would only have 3 electrons to itself, right? One from each bond. That would make it double positive. And it's not double positive, it's neutral. So we need to add 2 electrons to make it neutral. So we add an electron pair. Now that also fills its valency if you think about it, right? The nitrogen has 3 bonding pairs, so that's 6 electrons, plus the lone pair is 8. So the nitrogen has no pi bonds, and it has a filled outer shell, right? 4 pairs of electrons. If you didn't draw that lone pair in, you might be tempted to say that it was sp2 hybridized, but it's not. That lone pair is there, it fills the outer valency, and that means that nitrogen in ammonia is sp3 hybridized. So here we've got something that's called a carbocation. It's a central carbon that's positive, and then it goes on to bond to 3 hydrogens in this case. So again, you can immediately see there are no pi bonds on that carbon. What about unfilled orbitals? Well, the carbon here is actually positive, and that means that it's short an electron for the formal charge calculation. If you look at the carbon as it's drawn, it has 3 electrons to itself for formal charge calculation, right? Half of each bond. And that's 3 electrons, and carbon is in the fourth column, which means it needs 4 valence electrons for the formal charge to be 0. And this only has 3, which actually means it's short one, it's positive, and that's exactly the charge we see. That means there is no additional lone pair on this carbon. Think about it, if you put a lone pair on that carbon, it would actually give it 5 electrons for charge purposes. That would actually make it negative, not positive. But that does mean that this carbon in the methyl cation does in fact have an incomplete outer shell. It has an unfilled orbital. It only has 3 pairs of electrons surrounding it. And that means that there's an orbital that's actually empty. It has 4 valence orbitals, only 3 of which have electrons in them. So it has an unfilled orbital and therefore is sp2, right? We have to knock that p count down by 1. Note that it's not the positive charge that gives that carbon an unfilled orbital. It's the combination of the positive charge and where carbon lies in the periodic table. We'll look at another example in a minute that will kind of break you of that bad habit. So next we have this carbon surrounded by 3 hydrogens and a single electron. So again, no pi bonds, that's pretty obvious because there's no double or triple bonds. What about the total electron count? Does this have an unfilled orbital? Well, the total number of electrons surrounding that carbon is 7, right? 2 from each bond, and then that 1 extra lone electron, that dot. And 7 means that one of those orbitals is only half filled, right? Carbon has 4 valence orbitals, it can hold 8 electrons, this only has 7. So one of those orbitals is half filled, and that's not filled. It has an unfilled orbital. So we knock that p character down once for that one unfilled orbital. This carbon is sp2 hybridized. Now our last example, we have ammonium, the ammonium cation, NH4+. So let's take a look at this. Again, clearly there are no pi bonds sticking out of that nitrogen because there are no double or triple bonds. What about unfilled orbitals? Well, it's tempting to look and see that positive charge and say, hey, it's electron deficient, it must have an unfilled orbital. But that's not the case. Look at how many electrons surround that, both for charge purposes and for valency purposes. Nitrogen is in the fifth column in the periodic table, so it wants 5 electrons all to itself for a neutral charge. And as drawn, this only has 4, right? 1 from each bond. And, well, the nitrogen's positive. So that's exactly right? It wants 5 to be neutral, but it only has 4, so it's positive. But you see that for valency purposes, when we count all the electrons that surround an atom, this actually has 4 pairs of electrons, right? 2 from each bond. That means that it has a full octet of electrons surrounding it, which means that it does not have an unfilled orbital. So again, don't correlate positive charges to unfilled orbitals, right? We saw that that was the case with carbon, but with this nitrogen, yeah, it has a positive charge, but it doesn't have an unfilled orbital. It has a full octet. And that means that the nitrogen is in fact sp3 hybridized. No pi bonds and no unfilled orbitals. We leave it at sp3. Now remember, a covalent bond is simply a pair of electrons shared between 2 atoms. Now there's nothing that says that the 2 atoms have to share equally. Atoms can share electron density in a bond differently based largely on electronegativity. Electronegativity is simply an atom's affinity for electron density. And there are trends for electronegativity. If you look at the periodic table, electronegativity for a given element tends to go up as you move to the right and up in the periodic table, if we ignore the noble gases. So, for example, nitrogen is more electronegative than carbon. They're in the same row, but nitrogen's further to the right. Electronegativity can be quantified using the Pauling electronegativity scale, and it's a convenient scale. If you look at the most electronegative element, right, fluorine, it's the furthest to the right and the highest up, again ignoring the noble gases. Fluorine is the most electronegative element, and its Pauling number is roughly 4.0. So it's a convenient 4.0 scale. Now there is a second trend that dictates the electronegativity of any given atom, and that is the amount of S character in its hybridization. So again, looking at hybridizations of atoms is really important. The trend is that the more S character there is on an atom, the more electronegative it is. So here I have three different molecules with carbon in the three different stages of hybridization. We have methane with an sp3 carbon, we have ethene with a pair of sp2 carbons, and then we have ethyne with a pair of sp carbons. And because the ethyne has more S character, that is its sp, a half S in character, it's actually a more electronegative carbon than either ethene or methane's carbons. So when electron density is not shared equally in a bond, it creates an uneven distribution of charge, and that's called a dipole. And the magnitude of a dipole is called a dipole moment. And the extent of that dipole moment is calculated by the difference in charge, that is how much charge has been separated, multiplied by the distance at which it's been separated. So you can have a large dipole moment associated with either, a small charge that's separated but over a great distance, or a very large charge separation over a small distance. Now, when you have a bond where the two atoms do not share electron density equally, we call that a polar covalent bond. It's a bond, covalent bond, that has a dipole. And it's caused when you have two elements that are bonded together that have reasonably different electronegativities. A nice simple example is hydrogen chloride, HCl, right? Hydrogen, being far to the left on the periodic chart, has a relatively low electronegativity. Chlorine, being far to the right, has a much higher electronegativity. And that means that in that bond, the more electronegative chlorine is going to pull electron density away from the hydrogen. That creates a dipole, in which the chlorine is partially negative and the hydrogen is partially positive. These are not formal charges, they're just partial charges. There are a couple ways we can actually depict the polarization of a bond when we draw it out. If you need to call attention to the fact that there's a dipole, one way to do it is with sort of a notched arrow. We draw an arrow from one atom to the other with a little hash on the side of it. And what that's saying is that the electron density is being pulled in the direction of the arrow. It's kind of easy to remember because if you look at the other side of the arrow, it kind of looks like a little plus sign, right? And that means that, yeah, that side of the bond is actually being slightly positive now. Another way of calling attention to a dipole is to just draw out partial charges. So we use a lowercase delta followed by the charge, plus or minus. So don't confuse that with formal charges, right? These are partial charges. We have a partial positive charge on the hydrogen because it's the less electronegative atom in that bond, and then we have a partial negative charge on the chlorine because it has a higher electronegativity.